Right now, beneath one of Italy's most densely populated regions, something is fracturing from the inside out. Scientists monitoring Campi Flegrei have detected a disturbing pattern in the seismic data streaming from beneath Pozzuoli, a coastal town west of Naples, where 500,000 people live directly above a volcanic caldera that last erupted in 1538. The earthquakes aren't just shaking the ground, they're breaking apart a critical geological barrier deep underground, one fracture at a time, and the implications are keeping volcanologists awake at night. The Caprock, a fibrous layer of rock that sits like a pressure lid between 1 and 2 kilometers beneath the surface, is showing signs of progressive damage. Each earthquake that rattles through the region doesn't simply fade away into silence, it leaves behind microscopic cracks, stress fractures, and zones of weakness that accumulate over time. This isn't speculation. High-resolution seismic imaging conducted by Italian and American researchers has revealed a deformed caprock layer under increasing strain, with earthquakes originating within this very zone before migrating deeper into the volcanic system. For a supervolcano already experiencing the most intense unrest in recorded history, the degradation of this natural seal represents a boundary crossed, a threshold beyond which the familiar rules no longer apply. The numbers tell a sobering story. Since 2005, the ground in Pozzuoli has risen by approximately 1.4 meters. That's not a gradual drift. It's a relentless surge driven by forces accumulating in the darkness below. In the past year alone, the uplift accelerated by nearly 30 centimeters, and the seismicity has exploded. Over 1,000 earthquakes now strike each month, with the largest reaching magnitude 4.6 on June 30th, 2025, the strongest ever instrumentally recorded at Campi Flegrei. Earlier in the year, on March 13th, a magnitude 4.4 earthquake struck at 1:25 local time, followed by another 4.4 event on May 13th. As recently as early November 2025, residents of Naples and Pozzuoli felt a series of tremors that lasted longer than usual, buildings swaying for prolonged moments, while alarms and anxieties flared in the pre-dawn darkness. The municipality issued warnings. The National Institute of Geophysics and Volcanology confirmed what locals already knew. A seismic swarm was underway, and the caldera was far from finished. To understand what's at stake, you need to grasp what Campi Flegrei actually is. This isn't a single mountain with a neat cone and a lava-filled crater. Campi Flegrei is a 13-kilometer-wide collapsed volcanic caldera, a vast depression formed by catastrophic eruptions 39,000 and 15,000 years ago that expelled so much material the Earth's surface simply caved in. What remains is a scarred landscape of craters, fumaroles, and thermal springs, all sitting beneath a thriving urban sprawl that includes parts of Naples itself. The caldera's name translates to burning fields, a reference to the sulfurous fumes and ancient myths of the underworld that Romans believed lay beneath this ground. UNESCO recognizes its geological significance, but its true danger lies in its restless behavior. Unlike volcanoes that follow predictable cycles, Campi Flegrei experiences something called bradycism, slow vertical movements of the land driven by underground pressure changes. The last major bradyseismic crisis occurred between 1982 and 1984, when the ground in Pozzuoli rose by nearly 1.8 meters in just 2 years. Thousands of earthquakes shook the region, buildings cracked, and authorities evacuated entire neighborhoods. The historic center of Pozzuoli, the Rione Terra, was abandoned, its residents forced to watch their homes fracture under the relentless heaving of the earth. Then, as mysteriously as it began, the unrest subsided. The ground settled, the earthquakes faded. For 2 decades, Campi Flegrei slept, and scientists believe they understood the rhythm. Periodic episodes of inflation driven by magma or volcanic gases rising from depth, followed by deflation and calm. But in 2005, the ground began rising again, and this time it hasn't stopped. The current crisis, now stretching into its 20th year, has surpassed the 1980s in duration, and recent research suggests the mechanism driving it is far more complex and potentially more dangerous than anyone realized. At the heart of the mystery lies the Caprock, a geological feature that recent studies have shown behaves unlike any other volcanic seal on Earth. Stanford geophysicist Tiziana Vonario and her colleagues published groundbreaking research in Science Advances in May 2025 that fundamentally challenges how we think about Campi Flegrei's unrest. Through a combination of subsurface tomography, laboratory experiments, and decades of seismic data analysis, they discovered that the Caprock possesses what they call self-healing properties. When cracks form in this layer, interactions between the rock's minerals and hydrothermal water cause microscopic fibrous minerals to precipitate, rapidly sealing the fracture. fractures. Within 24 hours in laboratory conditions designed to mimic the geothermal environment beneath Pozzuoli, volcanic ash and crushed rock samples heated in a pressurized vessel formed mineral fibers that cemented cracks shut, transforming an open system into a closed pressure cooker. This self-healing behavior creates a deadly paradox. Every time the caprock seals itself, it traps more pressure below. Water infiltrates from the surface, seeping down through layers of porous rock until it accumulates in a geothermal reservoir sitting between 2 and 4 kilometers deep. There, temperatures reach 300 to 400 degrees Celsius, hot enough to convert liquid water into superheated steam and trigger chemical reactions that produce carbon dioxide. As these fluids accumulate beneath the sealed caprock, pressure builds and the rock layer begins to deform. It stretches, it strains, and eventually when the pressure exceeds the rock's strength, estimated at 45 to 74 megapascals depending on depth, the caprock fractures. The earthquakes that result aren't just symptoms of the pressure, they're the mechanism of release, violent ruptures that shatter the seal and allow liquid water to flash instantly into steam. The result is explosive bursts of vapor and boiling mud, accompanied by the booming sounds that have become a terrifying signature of life above Campi Flegrei.
But here's what makes the current situation so alarming. The earthquakes aren't releasing pressure fast enough to prevent accumulation. Instead, they're creating a feedback loop. Each fracturing event temporarily drops the fluid pressure, but because the caprock seals so efficiently, the pressure rebuilds quickly. Meanwhile, the cumulative damage to the caprock layer increases with every earthquake. High-precision earthquake relocations conducted by Italian researchers show that seismicity begins within the caprock itself at depths around 1 to 2 kilometers, then migrates downward over time as stress redistributes through the volcanic system. This downward progression is the opposite of what you'd expect if magma were rising from below. It suggests instead that the earthquakes are fracturing the caprock from within, progressively weakening the seal that contains the pressurized reservoir beneath. The seismic escalation has been relentless. In 2023, over 90% of earthquakes had magnitudes below 1.0, barely perceptible tremors that nonetheless added up to thousands of events. By 2024, the intensity jumped. A magnitude 4.4 earthquake struck on May 20 near the Solfatara area, recorded as the largest event since continuous instrumental monitoring began in the region. On March 13, 2025, another significant earthquake measuring 4.4 rattled homes and nerves. And just months later, on June 30, a magnitude 4.6 earthquake occurred offshore, surpassing all previous events to become the strongest earthquake instrumentally recorded at Campi Flegrei. These aren't just numbers. Each event sent shockwaves through buildings already weakened by years of continuous shaking. And each reminded residents that they're living on ground that refuses to stay still. The most recent swarms have been particularly unsettling. On November 9, 2025, a series of earthquakes beginning at 6 a.m. shook Naples and Campi Flegrei, the strongest measuring magnitude 2.2, but lasting unusually long, causing buildings to sway for extended periods. Reports of intense shaking came from the neighborhoods of Agnano and Fudigrotta, areas built directly over the caldera's most active zones. In the week leading up to mid-November, 211 earthquakes struck the region, with magnitudes reaching 2.5. The pattern is clear. The caldera isn't calming down, it's accelerating towards something, and scientists are racing to understand what that something might be. Advanced imaging technologies have given researchers an unprecedented view of Campi Flegrei's internal architecture. Using earthquake waves as a natural CT scan, teams led by Grazia Delandro at the University of Naples Federico II and collaborators at Stanford have mapped the subsurface in 3 dimensions, revealing a complex structure that explains much of the observed behavior. Recent analysis shows that some of the larger events, including the March 13th earthquake initially recorded as magnitude 4.4, were actually compound sequences consisting of multiple closely timed shocks rather than single large ruptures. At depths between 2 and 4 kilometers lies a gas-enriched reservoir, imaged as a low-velocity zone where pressure and temperature create a chaotic mix of steam, water, and carbon dioxide. Directly above this reservoir, between 1 and 2 kilometers deep, sits the deformed caprock, identifiable by its distinct seismic signature and the concentration of earthquake epicenters within its boundaries.
Beneath 3.5 kilometers, the basement rock provides structural support, but it's the interaction between the gas reservoir and the fractured caprock above it that drives the surface deformation and seismicity. Recent studies have also identified what researchers call a weak layer in the crust, a zone damaged by older magma intrusions that now traps rising gases and fluids. This layer, sitting between 2.5 and 3 kilometers deep, acts like a sponge for pressure, accumulating stress until it exceeds the rock's tolerance and triggers fracturing. The largest earthquakes in recent years have occurred along faults that border this zone, suggesting that as the reservoir depressurizes through fracturing, the stress redistributes to the caldera's ring faults, structures left over from ancient collapses that are being reactivated by the current unrest. The water connection represents one of the study's most important revelations. For decades, volcanologists assumed that uplift and earthquakes at Campi Flegrei were driven by magma or volcanic gases pushing upwards from depth. But the Stanford research, corroborated by studies published in Nature Communications and Communications Earth Environment in 2025, challenges this narrative. By analyzing 24 years of rainfall data and subsurface hydrodynamics, Venorio and her colleagues found that increasing precipitation over the past 2 decades has led to greater groundwater recharge in the volcanic system. It's not the rain itself that causes earthquakes, it's the slow, steady recharge of the geothermal reservoir by infiltrating water, which then becomes trapped beneath the self-sealing caprock. As rainfall rates have increased due to climate variability, the rate of pressure buildup has accelerated, explaining why the current unrest has intensified despite no evidence of fresh magma intrusion in the shallow crust.
To test this theory, the researchers conducted experiments using a device that functions exactly like a moka pot, the iconic Italian stovetop espresso maker. They filled the bottom chamber with brine to simulate the geothermal reservoir, packed the filter section with volcanic ash and crushed rocks typical of Campi Flegrei to represent the caprock, and heated the apparatus to temperatures matching those at depth. Within 24 hours, mineral fibers formed in the rock layer and cracks sealed through cementation. When pressure built to critical levels, the system fractured explosively, with liquid water flashing to steam and escaping in violent bursts. The parallel to Campi Flegrei is uncanny, a system that seals itself, pressurizes, and fractures in cyclical patterns, driven not by rising magma, but by the physics of water, heat, and rock. So what might happen if the caprock continues to degrade? Scientists point to several possibilities, though the uncertainty remains high. The most immediate concern centers on a phreatic explosion, a steam-driven eruption caused by superheated water flashing to vapor. Unlike magmatic eruptions that require molten rock to reach the surface, phreatic explosions can occur when pressurized fluids breach a weakened seal, ejecting steam, boiling mud, and volcanic ash without any magma involvement. Historical records suggest Campi Flegrei's last eruption in 1538, which created the Monte Nuovo hill, was precisely this type of event, a sudden, violent release that lasted 8 days and buried the landscape under meters of debris. Based on what scientists know about the current strain on the caprock, the conditions for a similar phreatic eruption could be developing, though predicting when or if such an event will occur remains beyond the reach of current monitoring capabilities. The implications extend beyond immediate eruption risk. Progressive damage to the caprock affects how stress distributes through the caldera, which scientists believe could potentially reactivate faults that haven't moved in centuries. Research published in Journal of Geophysical Research in October 2025 analyzed the preparatory phases of 20 major earthquakes at Campi Flegrei since 2020, finding that a measurable increase in residual strain in the days before each event correlates directly with the magnitude of the subsequent earthquake. This discovery suggests the possibility of short-term forecasting. If scientists can monitor strain accumulation in real time, they might be able to predict the magnitude of upcoming earthquakes days in advance, giving authorities critical lead time for emergency planning. However, this capability remains experimental, and the unpredictability of how the damaged caprock will respond to continued pressure makes long-term forecasting deeply uncertain. The Italian government and civil protection authorities are acutely aware of the escalating risk. Current alert levels remain elevated, though not at the highest tier that would trigger mass evacuations. Seismic hazard assessments, updated in 2024, now consider the possibility of earthquakes reaching magnitude 5.1, significantly larger than anything recorded in recent decades and powerful enough to cause widespread building damage in Pozzuoli and surrounding areas. Building retrofitting initiatives have been proposed to bring residential structures up to modern seismic standards, with studies suggesting that reinforcing common buildings could reduce fatality risk by over 70% even if larger earthquakes occur. But implementation faces enormous challenges in a region where much of the housing stock consists of old masonry structures built long before earthquake-resistant design became standard. Proposed mitigation strategies focus on managing the root cause of the pressure buildup. Venorio and her colleagues suggest that reducing groundwater levels or channeling surface runoff away from infiltration zones could slow the recharge of the geothermal reservoir, potentially stabilizing the system. Extracting fluids from wells drilled into the reservoir could directly reduce pressure, though this approach carries its own risks. Too much extraction could destabilize the surrounding rock, while too little might have no effect. These are not simple engineering problems. They're questions about intervening in a natural system that operates on geological timescales with forces measured in megapascals and temperatures hot enough to melt steel. For the people living above Campi Flegrei, the abstract language of scientific papers translates into daily anxiety. They feel the tremors, they hear the booming sounds when Caprock fractures deep below. They watch hairline cracks appear in their walls and wonder if the next earthquake will be the one that brings the ceiling down. They know their homes sit on land that has risen nearly 1.5 meters in 2 decades, that their town center was evacuated once before and could be again. They live with uncertainty measured in seismic graphs and official statements that oscillate between reassurance and alarm. And they know that beneath their feet, pressure is building, the caprock is fracturing, and the outcome remains unwritten. The question that haunts Campi Flegrei isn't whether the caprock is damaged. Multiple studies using different methods have confirmed that it is. The question is how much more damage it can sustain before something gives, and what form that giving might take. Several scenarios are possible, though none can be predicted with certainty. The caprock could fail catastrophically, triggering a phreatic explosion that reshapes the landscape in days. The accumulating strain could finally exceed the capacity of every fault system in the caldera, producing an earthquake larger than the region has seen in modern history. Or the system could find a new equilibrium, venting pressure through continued small earthquakes and fumarolic activity without tipping into disaster. Right now, with data streaming from hundreds of sensors and researchers publishing new findings every few months, the honest answer is that no one knows which path the caldera will follow. What's clear is that Campi Flegrei has entered a phase of unrest that surpasses historical analogs in both duration and intensity. The ground has risen higher and more persistently than in previous recorded episodes, the earthquakes have grown stronger, and the caprock that once contained the system's pressure has been progressively damaged by the very forces it was meant to control. The self-healing properties that make the caprock unique also make it dangerous, creating a cycle of sealing and fracturing that drives the caldera toward an uncertain endpoint. Every earthquake is both a release and a wound, a momentary drop in pressure bought at the cost of structural integrity. And with 500,000 people living above this fractured lid, the stakes couldn't be higher. The Earth is speaking in the language of seismic waves and ground deformation, telling us that something profound is happening beneath southern Italy. The scientists listening to that language are doing everything they can to interpret the message, to understand whether the damaged caprock signals an imminent crisis or a prolonged period of elevated but manageable unrest. The data they've gathered points to a system under unprecedented stress, but the translation from observation to prediction remains incomplete. The Earth doesn't operate on human timescales or care about our need for certainty. It moves when the forces within it demand movement, and all we can do is watch, measure, and prepare for possibilities we can't fully predict. If you found this examination of Campi Flegrei's unfolding crisis eye-opening, subscribe to stay informed as this story develops, because the ground beneath Naples is still moving, the caprock is still fracturing, and the next chapter in this supervolcano's history is being written beneath our feet right now.